Okay, so here's the deal today. We're looking at geometry notes 11.7. This is our last set of notes before the test on Tuesday. Okay, we got a test in 2 days. We got class on Friday. We're going to do the review. We got Monday class. We got to review to finish up. I got a quiz on Friday that you'll take, and then I'll give it back on Monday. We'll go through the first quiz tomorrow as well, right away. And my purpose of getting you ready for this thing is that you're successful. Okay, it's not about, just another test, because if that was the case, I would have given you all the tests together. Make sure you're getting your stuff done. Make sure if you've got questions, you ask them. I'm here tonight after school. For those people taking off early, if you've got time tonight after school, you can take that quiz before you go. Okay, now, objective, to compare and find the areas and volumes of similar solids. Okay, similar solids have the same shape and all their dimensions are proportional. The ratio of corresponding linear dimensions, length, width, height, of two similar solids is the scale factor. Gosh, this sounds like we've done this before, right? We did, section 10.4, okay? Any two cubes are similar, as are any two spheres, because they only have one dimension that we have to make a transfer to get to the other, or a changeover. So here are the two rectangular prisms similar. How do we check similarity? First, we compare corresponding sides. And since the beginning of the semester, January, we were talking about corresponding sides. So we're talking here about 3 to 6, 3 to 6, and 2 to 4. Are these similar? And how I can tell that they're similar is that corresponding sides have the same ratio, the same perimeter ratio, which is side ratio, and scale factor, they're all the same value when we're talking about them. Okay, and I'm going left to right, first figure, the second figure, as I do this. Okay, now in B, I am looking at the fact that I'm making the comparison of sides. So I've got this going on here. I've got 2 to 3, 2 to 3, and 3 to 6 is not the same as 2 to 3, because 2 to 3 is 2/3. 3 to 6 is 1/2. They are not similar at all, and that's how you make this connection. Now remember, I'm comparing all the corresponding sides combinations as I do this. Okay, it's not just one or just, well, okay, one works, it's done. No, you can't make that determination until you compare all of them. So make sure you're getting that done. Okay, are there any questions at this point for problem 1A or B? Now, remember, in 10.4, we talked about scale factor's relationship to area. And that scale factor relationship to area, scale factor is A to B, area is A squared to B squared. We just take the scale factor and square it. The scale factor's relation to volume, A to B, the scale factor, is related to the volume ratio as A cubed to B cubed. And that kind of makes sense, because of the relationships. But you got to be careful as you're going through these. I'm asking you to set up proportions today. It's a combination of chapter 7 and 10.4 and now 11.7. So make sure you realize it goes back to all the stuff we've done since January. Now, are the two cylinders similar? I'm going to compare shape 1 on top to shape 2 on the bottom. Well, when I'm making this comparison here, I got 12 to 10 for my sides, my heights, and I got 6 to 5 for my radiuses. So I've got the radius of shape 1 to the radius of shape 2. I've got the height of shape 1 to the height of shape 2. And if they're going to be similar, they have the same ratio comparing corresponding sides from one shape to the other. And it has to be from one shape to the other. This is yes, because it ends up being 6 to 5. Okay? And I put shape 1 on top, shape 2 on the bottom, so I reduce and I know that the scale factor is 6 to 5 as I step through this. Are there any other questions about this? Now, today's assignment, you will be asked to identify scale factor. first shape the second shape, or second shape the first shape, big to little or little to big. Pay attention to those directions. When I do B, I'm still doing it. I'm just going to go 1, 2, and 3, 2, 4, and 6. And I'm going to check it out. Are they the same? This is 1/2, 1/2, 1/2. They are the same scale factor, so they are similar. And notice I'm answering all of the question. I'm not just gibberishing my way through it and making it look like I'm getting it done. Please, 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 please make sure you show your work and show your final decision making on these. Now, how do I do some of this stuff? I'm just going corresponding sides. That's the secret. I pick one side first, or one shape to be first, one shape to be second, and the first shape's on top, second shape's on the bottom. Like this one, I'm going to compare cone 1 to cone 2. Okay? In comparing cone 1 to cone 2, I can determine whether they are similar or not. So in doing this, I look at cone 1 and it's got a height of 30 and cone 2 has a height of 35. Cone 1 has a diameter of 20 and cone 2 has a diameter of 25. I'm going to use those. And I'm telling you right now, I kind of gave you a hint. They're not congruent, okay? They are not equal, I should say. I suppose not congruent. 30 to 35. That reduces the 5 to 7. And 20 to 25 reduces to, or 6 to 7, and 4 to 5, and those are not the same, so they can't be equal. So I know they are not similar based on that information. Now I'm going to compare cone 1 to cone 3 if I get this open, and that cone 1 is 30 and that's 45 for cone 3, 20 to 30, and those are the two values I'm checking. Well, I reduce them here, 2/3 and 2/3. Well, gosh, they're the same value. Consequently, my conclusion is that they are similar. And I'm going to answer the question. They say, hey, which two of the following cones are similar? Answer that question is cone 1 to cone 3. What is their scale factor? 2 to 3 is their scale factor as I go through this. 2 to 3 is their scale factor. That's how I make the determination. Now at this point, as people are writing this down, they're looking at it and going, well, Bloom, what about cone 2 to cone 3? You didn't check that one. I don't have to. Since cone 1 is similar to cone 3, I already know that cone 3 can't be similar to cone 2 because cone 1 is not similar to cone 2. Two shapes that are similar to each other are also similar to other shapes that one of the other is similar to. If one of them isn't similar to another shape, then neither are similar to the other shape, okay? Now, this is why we're here. What I've done on the previous screens is just review all the stuff we learned from 10.4, okay? All the information from 10.4 has been reviewed, and our setups, we're golden as we go through. Now I need to make sure you recognize that Theorem 11.12, areas and volumes of similar solids. If the scale factor, this is from 10.4, perimeter ratio, of two similar solids is A to B, then the ratio of their corresponding areas is A squared to B squared. Remember, area is a squared unit, so A squared to B squared. The ratio of the volume is A cubed to B cubed. Okay, well, volume is cubed. Well, I want you to keep in mind as we're doing this today, according to 11.12, if I line up, say, two corresponding sides in this, if I say 2 to 4, and I line those up, I got 2 to 4, they reduce to be 1 to 2. That happens to be my scale factor. According to what we just read in 11-12, excuse me, not 11-2, 11-12, areas and volumes, the area ratio should be 1 squared to 2 squared, which would be 1 to 4 is my ratio, okay? According to that theorem that we just looked at. And according to the theorem that we just looked at, if I take my perimeter ratio, which is my scale factor, and I cube it, I can get my volume ratio, which is 1 to 8. Now, I've got a lot of people that every time I do this, they're like, Bloom, there's just no way. I mean, if we put real numbers in there, it ain't going to work that way. Well, keep in mind the scale factor, if the real numbers, we had 1 to 2, right? And that's where it's going. I mean, that's pretty straight up. But now, the area, they gave us area. They gave us area right here. We got 22 to 88. Well, if I put 22 to 88 in there, does that reduce to something? Check it out. It reduces the 1 to 4. And people are like, no way. That's the same as what we'd expect because our scale factor was 1 to 2 and its squared is 1 to 4. And we took the actual areas and it's the same. Well, let's take the actual volumes. I bet you it don't work on volumes. Okay, so I got 6 to 48 because I got that, the actual volumes, they're right there. 6 to 48, that reduces the 1 to 8. No. Crazy. So it does work. So here's the thing that we're getting out of this. When we compare the ratios, we know all ratios are related to the scale factor. Okay, so it's a nice piece of knowledge to have for us to find missing pieces of other areas, other volumes. Okay, so long as we have scale factor. Now I'll wait for you guys to all get that down. Now remember, tonight after school, Thursday night, 5/11, I am going to be here for any type of student help if you need it. Okay, if you just need a room to sit and do your stuff because when you get home you can't focus or you get distracted, hey, this is the place to be. I ain't that distracted and I'll play classical music the entire time. Okay, you will work diligently to get out of here. I know you will. Okay, so make sure you come on in. Now, here's the deal. How do we use these things? How do we use this knowledge of scale factor of A to B, area ratio, A squared to B squared, volume ratio, A cubed to B cubed? The square prisms are similar. What is the scale factor of the smaller prism to the larger prism? Now here's the deal. This is a situation where I'm given volumes. I have volume provided right there. Now, remember the ratio relation? If I have volume, I take the cubic root. Cubic root. I take the cubed root of a volume and I get my scale factor. They want scale factor. So I'm just going to take the cubic root in my calculator. That's my volume ratio and I'm taking cubic root. And it's the cubic root of the volume ratio is equal to scale factor. That's what I know. Okay? But I got to be able to do that in my calculator. So pop that puppy out and find your math key, because your math key can help you out if you got a great graphing calculator. If you don't have one, don't worry, I'll show you another method. The graphing calculator has something there, the cubic root. It's number 4 or number 3 going down when you hit the math key. I think it's frac, square root, cube root, quad root, but I could be wrong. Okay, now once you hit that, it'll come up in your calculator and you just put 729 in it. Okay, and it kicks out what does it kick out? Is that a 9? Okay, and then if I put in the cubed root of 1,331, it should kick out an 11. So that cubed root of 1,331 should kick out an 11. So I now have scale factor. Wow, that's pretty cool that was that close. Okay, but I now have scale factor as we go through. Okay, and I found it by using the cubed root function. But it makes sense. If I take my scale factor and cube it, I should get the 729 1,331st. Okay, now it's your turn, but I'm going to let you in on a secret on how I do these. Reduce before you take the square root. Go, get her done. Use your calculator, help yourself reduce before you take the square root. Make sure it's out, make sure you're operating with that puppy. I find that it's fat fingeritis that interferes with people's success here. It's nothing else. And that's a malady they cannot correct through surgery. Yeah, go ahead and use that one. Okay, make sure that you're careful. Fat fingeritis is corrected through practice and care as you're pushing buttons. It's a non-surgical procedure. It's a nice thing. Everybody can be cured of fat fingeritis. Now, keep in mind, in problem 4, what is the scale factor of two similar prisms with surface areas 144 meters squared and 324 meters squared? First of all, I have an area ratio. I'm going to use fractions to reduce. They reduce to become 4/9. That is still an area ratio. So I take that area ratio and find its square root to find scale factor. Okay, and that's 2 to 3. But now I've got some folks, and by a show of hands, how many people took the square root of 144 and the square root of 324? Pretty ugly, that square root of 324, wasn't it? What was the square root of 324? It was 18. Well, it wasn't ugly. You got a scale factor of 12 to 18. But wouldn't it reduce to 2/3? So always go down to the reduce. And even if you had weird funky decimals after you took the square root, if you put it into your fraction function in your calculator and had it become a fraction, you divided them out, it would actually take that extra commonality up and make it a fraction, which would be our scale factor. Okay, so it's kind of neat that it'll work that way, but unfortunately, if you don't know how to use a function in your calculator, you can't. So we got to practice so that we can become better at using a tool that we get to use on most of our tests. So in 5, I'm going to skip. 6, we're going after 6. The volume of two similar solids are 128 meters cubed. 128 meters cubed. I got to get rid of that green thing. It's just not going anywhere. 128 meters cubed. Well, wasn't that interesting? Let's undo that. Sorry guys, we're just gonna have to get this board task. I've got like 3 problems left and being kind of persnickety on this one. Hey, for those people at home, it's just like you're in class. There it goes, it's out of there. Okay, but 128 meters cubed and 250 meters cubed, that's a volume ratio I can set up, right? It's all about volume. People, how do you know? Because they're cubed. It's volume. So if I set up that volume and I reduce, okay, I have a habit of reducing before I take square roots or cubed roots, okay? It makes my life easier. So now I've reduced them and I still have a volume ratio. A lot of times when people go, oh, I've done a lot of work on that balloon, it must be done. No, focus on what you have and where you have to go to get our next step. So we need to take our volume ratio and take its cubic root to find scale factor. So our scale factor is 4/5. Now, it's all about what they're asking me to find. So I'm rereading the question. The volume of two similar solids are 128 meters cubed to 250 meters cubed, and we found their scale factor 4 to 5. What is the surface area of the smaller solid if the larger one is 250 meters squared? Now these are not the same number because one's cubed and one's squared. They're talking about surface area in the second one. Now I know that the relationship between scale factor and area ratio is when I take the scale factor and square it. So I've got 4 squared and 5 squared. I know that's 16 and 25. I just wanted to make sure you knew where I got 16 and 25. Now, from chapter 7, I set up ratios. Okay, and chapter 10, I set up a specific ratio to solve for area. Well, I'm setting up a specific ratio to solve for area. Here they tell me the surface area of the larger solid is 250. And now people go, well, where do you put it? My question to you is, which number's bigger, 16 or 25? And you go, well, duh, Bloom, 25. Well, 250 goes on the bottom then. I have a ratio of 4 squared to 5 squared. I set it equal to x over 250. Now I solve this proportion. Now I cross multiply 16 times 250 divided by 25, and I get 160. And word problem, word answer, there we go. Surface area of smaller solid is 160 meters squared. Maybe somebody should have said of the smaller solid. So let's say that. Any questions on how I did it? You will be asked to do these today. Tony, what do you have?
Oh. Well, the isn't really necessary.
We're good. It still works. Any others?
Oh.
Anything else? Okay. So, are we okay with how 160 was arrived at? Because remember, 160 is equal to x. Now, we've got our next set. On the next page, I've got a little notes on capacity. So we're going to look at capacity, and we're going to talk about doing a monstrous problem. So as we go through this, I'm going to pop that stuff down. I got capacities and weights of similar objects can be compared. Capacity of an object is the amount of the fluid the object can hold. The capacities and weights of similar objects made of the same material are proportional to their volumes. Okay, they're proportional to their volumes. A bottle that is 10 inches high holds 34 ounces of milk. Okay, that's information. The sandwich shop shown at the right, that's this little picture over here, is shaped like a milk bottle. To the nearest 1,000 ounces, how much milk could the building hold? Now, keep in mind that this milk bottle has the same dimensions proportionally as our milk bottle that holds 34 ounces. We have 10 inches and we have 480 inches. Those are our corresponding side measures, and we're assuming that these are similar figures. So now I've got my A to B, which is my scale factor, reduced, which is 1 to 48. Remember the connection between scale factor in area and volume. Since I am doing a volume problem, I must find the volume of my cube. So I got to do the scale factor of volumes. So remember, if I take the volumes, I'm going to take A cubed over B cubed. And to achieve that from 1/48, it's 1 cubed over 48 cubed. Okay. Now, I just have this here to make sure you recognize I'm finding volume. Okay. Do I have information about capacity in the problem? Okay, I need one of them, otherwise I won't. I mean, because if the original held like 5 ounces, then I could find it. Okay, if the original held like 1,000 ounces, then I could find the other. In this particular case, the original holds 34 ounces. Do you see it? So in the original, it's a 34-ounce bottle of milk. Well, that's a small. I want to find the capacity of the large with volume. That's why we're using the volume ratio. At this point, we do a cross multiplication and solve. Go ahead, solving for x. You guys got it, you're on. By the way, just take 48 to the third power. That'll help with that multiplication. I just wanted to make sure you guys know where 48 cubed would have come from, and that's from scale factor. Are you okay? That's me 48 cubed times 34. And then when I multiply it out, a lot of people go, no way. That's 3,760,128 ounces, Bloom. And I'm going to reread my question because they asked me to round to the nearest 1,000 ounces. So really my answers that because I go to the thousandth place, which is right there, and right there is 1, so I just cut off the 128 and it's 0, 0, 0. Okay, so that's my ounces of milk. Now, every time I throw out a big number like this for you guys, I always got students kind of glaze over. So let's talk about it for a second. Sanborn, how many gallons of milk do you think you could drink in a week? I mean, you know, don't like go crazy guzzling like stuff, but what you normally go through in a week? 2, okay, all right. So if we go 2 gallons of milk, all right. But and a gallon is 128 ounces. So let's get this million of ounces down. So we're going to take this 3,760,128 ounces of milk, and we're going to multiply it by the fact that 1 gallon is equal to 128 ounces. So if y'all could do this on your calculator, it'd be cool because ounces are gone and I'm looking at gallons. So take that 3,760,128 ounces, divide by 128 ounces, and it'll give us gallons. How many gallons that represents? How many gallons is it, Dante? 29,376 gallons. Okay, 29,376 gallons. Knowing that right now without doing any calculations, how long is that going to take you to drink? Will you still be alive when you're done?
Yep. Oh.
Let's see it. Because we went, that's gallons, and you said 2 gallons a week, so let's make it weeks. So you've got 2,706, 29,376 gallons, and we were going, well, you know, in 1 week, I could drink 2 gallons, no problem, okay? No problem, all right? So you knock out gallons, and we are going to get our answer in weeks. So how many weeks is left? 14,688 point something. Okay, great. This is weeks, right? How many years is that? There are 52 weeks in a year. One year, 52 weeks. You okay with 288? Is that what we get? 282 point what? 146? 0.46 years. If I put 2 people on this project, the milk drinking project, it's 141.23 years. I'm getting close, right? Now, I always like doing stuff like this because when we talk about millions, we're always talking about billions and millions and just how much that really is. It's crazy, right? We're done with notes, but I just wanted to say this was on our side of like how long it would take us to drink that much milk. I think after the first week it would curdle, a couple of weeks it would be bad, but you know, assuming it was perfectly refrigerated, okay, and you know, we could keep drinking for the next 282 years, okay? But that's what we've got for notes today. And what I'd like you to do next is take out your assignment. For those people at home, thanks for your time. Hope everything's going well. If you got questions, talk to Bloom at class.